Good morning, students. Today we will discuss Module 5. In Module 5, there are two chapters. One is compressors, other one is steam nozzles. So, under the compressors, basically we are going to study here the reciprocating compressors. So, what are the under the reciprocating compressors? The operation of single stage reciprocating compressor, work input through PV diagram, steady state flow analysis, effect of clearance, volumetric efficiency, adiabatic, isothermal, mechanical efficiencies. Then multi-stage compressors, what is saving in work by using multi-stage compressor, optimum intermediate pressure, intercooling, minimum work for compression. Then under the chapter nozzles, steam nozzles, the following topics will be dealt: flow of steam through nozzles, shape of nozzles, effect of friction, critical pressure ratio, supersaturated flow. So let's begin with the compressor, the chapter compressor. So to begin with, what is a compressor? Compressor is a mechanical device used to increase the pressure of a gas. The gas can be refrigerant or an air. So any gas. To component used to increase the pressure is called a compressor. The compressor broad classification can be classified into two categories. First, based on the working principle. First one is called a rotodynamic type compressor. Second one is called a positive displacement type compressors. Further, compressors can be classified into different groups. The following flowchart shows the different classification of the compressors. To begin with, compressors are basically divided into two types: positive displacement and dynamic. So under positive displacement, there are two categories again: rotary and reciprocating. Under rotary, there are different types of compressors: lobe, screw, liquid ring, scroll, vane. Under the reciprocating compressors, there are three types: diaphragm, double acting, and single acting compressors. So if you look at the rotary dynamic compressors, there are two types. One is centrifugal compressor, second one is axial compressor. So this is a broad classification of compressors. Let's go to the working principle and construction of a reciprocating compressor. So what is a compressor and how it is different from a pump? So if you know that pump is also used to increase the pressure, but the difference between pump and the compressor is pump handles the liquid, whereas a compressor handles the gases. As gases are compressible, the compressor reduces volume of the gas, whereas liquids are not compressible. Therefore, when liquid passes through a pump, its volume does not change, only its pressure increases. Liquids are relatively incompressible. While some liquids can be, there can be some exceptions on liquids, but most of the liquids are incompressible. What are the applications of compressors? There are many applications of compressors. Okay? They are used in a day-to-day life. So if you take domestic applications like air conditioners, air conditioners used in car and home, right? Uh, Home and industrial refrigeration makes use of compressors. Then hydraulic compressors for industrial machines, air compressors for industrial manufacturing. So these are some of the applications of compressors. So for this animation shows the working of a compressor. Hmm. So there are a multi-cylinder compressor, okay, so which is used to get a high pressure air. So if you look at parts of the compressor, there is a piston, cylinder. This is the main part of the compressor where piston moves back and forth and thereby results in a increase in the pressure of air. It is connected to a cross head, and cross head is in turn connected to a crankshaft, and the crankshaft is coupled to a rotor. So the crankshaft is rotated by driving motor, then it moves the piston up and down or back and forth, then resulting in the compressed air. So let's look into the working principle of the compressor. Following this block diagram shows the working principle of a compressor. If you look at this block diagram, there is a piston, there is an inlet valve and an exit valve. So when the piston moves from the inner dead center to outer dead center, or it is inner dead center is also known as the top dead center. If I keep the compressor vertical, then it is called a top dead center. So when the piston moves from inner dead center or top dead center to the outer dead center, it displaces the volume, right? At that time, the inlet valve will be open, so pressure inside the cylinder will be reduced, therefore it will suck air from the outside. So from the outside air will gush into the cylinder and occupy this volume. Then in the another half rotation of the crankshaft, piston will move from the bottom dead center to top dead center, or in other words outer dead center to inner dead center. When that happens, the both valves will be compressed, both valves will be inlet and exit valves will be closed, so the air volume reduces and the pressure increases. So at the end of the compression, exit valve will be open. So when this exit valve opens, high pressure gas leaves the cylinder and goes to the receiver. This is how a low pressure gas is compressed to high pressure gas. When it gets compressed, its volume decreases. This is how a compressor functions. So basically, you can call it as it is a piston. A compressor can be called as a piston and cylinder device with an automatic spring controlled inlet and exhaust valves. Okay. So there is a clearance between piston crown and the top of the cylinder. So if you see here, there will be some clearance. Okay. So the piston, the meaning is piston cannot displace the entire volume. There has to be some clearance volume. There will be some high pressure gas that will remain inside the cylinder at the end of the exhaust stroke. Okay. So this is the working principle of a compressor. So let's look into an ideal, that is what we saw is an actual compressor, how it works. But the actual compressors are very difficult to study, mathematically model and study. So therefore, as usual in as we do it in other parts as subjects of thermodynamics, we try to idealize so that it becomes easy to handle mathematically. So following are some idealization we incorporate. So there is an ideal reciprocating compressor. What do you mean by an ideal? I call an ideal reciprocating compressor if it satisfies the following conditions. So what are they? First one is the clearance volume is 0. There should not be any clearance volume. Then I call it as an ideal reciprocating compressor. What is the meaning of this? How it affects? Suppose if I did the clearance volume is 0, that means at the end of discharge process, the volume of gas inside the cylinder is 0. Right? So there won't be any high pressure gas inside cylinder at the end of a discharge. Right? This is the first condition. Second condition, no pressure drop during suction and compression process. So when in actual compressors, when the suction process happens, the pressure inside the cylinder will be less than the outside pressure, okay, or the inlet pressure. The whatever the pressure of the gas is there at the inlet, the cylinder pressure will be less than that. Okay, there will be a pressure difference between inlet pressure and the inside cylinder pressure. So in an ideal compressor, this won't be. The suction pressure will be equal to the outside pressure. Okay. So similarly, when there is a during the discharge, the pressure of the inside cylinder, the pressure inside the cylinder and the receiver, high pressure gas which is received by a cylinder, that pressure and this pressure will be same. Okay, which is not the case in a real world. So this is an assumption, important assumption. Okay, we assume that suction and no pressure drop occurs during a suction and compression. The third assumption is suction, compression and discharge are reversible and adiabatic, which is not the case. In actual cases, these processes are not reversible, but we assume that suction, compression and discharge, all three processes are reversible in nature. So when these conditions are satisfied, such a compressor is known as ideal reciprocating compressor. So let's look at the PV diagram of a ideal reciprocating compressor, because basically if you look at compressor, in a compressor what happens is work is done to increase the pressure, right? So we have to spend work to increase the pressure. To get a high pressure gas, we don't get it easily. Yeah, we have to spend some work. So we know that work is a high grade energy. So the minimization of work for getting a high pressure gas is an important criteria in design of any compressor. Therefore, study of work done in compressing the air becomes very important. We have to do that. So let's look at the work done in the compressing the gas. So for that we will draw PV diagram. So let us look at the PV diagram of that. So let's begin with the compression stroke. Let's say the cylinder is at the outer dead center, that I call it as a state 1. Okay, as the crankshaft rotates, it pushes the cylinder inside. Now here both exhaust and the inlet wall are closed. So when both exit and inlet wall are closed, so piston is moving. So that means the volume available for the gas is reducing as the piston moves inside. So therefore, when volume reduces, naturally it leads to a increase in pressure. Okay, the increase in pressure, it can have any the process of increase in pressure from 1 to 2 can follow different paths. It can be a polytropic process, or it can be an adiabatic process, or it can be an isothermal process, provided if there is a heat transfer. If we can transfer heat during the compression process, the process can be isothermal, or it can be an adiabatic if there is a heat transfer, or it can be any polytropic process. So when from state 1 to 2, air is compressed. Okay, at 2, the exit wall is open, and the high pressure air leaves the cylinder and goes to the receiver. Okay, so then piston moves and reaches the inner dead center. During this process, 2 to 3, the process 2 to 3 happens at a constant pressure. From 1 to 2, it can be some polytropic process. 2 to 3 is a constant pressure process. Okay, so then once again 4 to 1 is a suction process. During suction process, exit wall is closed, inlet wall is open, fresh air is drawn inside. Okay, it happens at a constant pressure. The pressure inside cylinder is equal to the outside pressure for an ideal process. So this is how the process takes place. So if you look at the PV diagram of the process, the area enclosed by the curve will be the work done during this process. The work done during compression is obtained from if you calculate the area enclosed by the curve. So this we have studied in the basic thermodynamics. To get the work done, what we have to do? We have to find out the area enclosed by process 1, 2, 3, 4, 1. So how to calculate this? We have to calculate the area of this cycle. So for that, so let's look at the important performance parameters of an ideal compressor. So the first one is volumetric flow rate. The volumetric flow rate of the compressor is very important parameter, because it tells us the quantity of air that is getting compressed, or quantity of air that is available for us. So that is very important parameter. The volumetric flow rate at the suction condition is equal to the compressor displacement, or the rate of swept volume. So for ideal compressor, the volumetric flow rate is equal to displacement rate, or the rate of a swept volume. So what is swept volume? So when the piston sweeps from inner dead center to outer dead center, volume that it sweeps, that is called a swept volume, or it is also known as a displacement volume. Okay, so this displacement volume, the rate at which volume is displaced will be equal to the volumetric flow rate of the compressor for an ideal compressor. Okay, so what is this swept volume? So swept volume for compressor is given by the area of the compressor, area of the piston, that is pi d square by 4, into displacement length, that is the distance between an inner dead center and outer dead center, that is L. So pi d square by 4 into L will be the displacement volume per cycle, or per revolution of the crankshaft. Suppose there is a N is the RPM of the crankshaft, then N N is the rotational speed of the crankshaft, then you get that is N into N. If there are the N number of cylinders, then the small n is the number of cylinders, then you get this, the swept volume will be equal to N into capital N pi d square into L divided by 4. So here the volumetric flow rate will be meter cube per minute. If you want a meter cube per second, then you have to divide this RPM by 60. Okay. So if the RPM is in the revolution is if either the n should be in the revolution per second. If the revolution is given in RPM, then n should be divided by 60. Then you get the meter cube per second. Okay. So this the volume the swept volume will be the volumetric flow rate will be for an ideal compressor will be equal to the swept volume. This is an important parameter. Please note this. For this, the volumetric flow rate is equal to the swept volume only for an ideal compressor, which has no clearance volume. If you take a real compressors which have clearance volume, the volumetric flow rate will not be equal to swept volume. That part we will study in the next part. But the time being, you please note that this volumetric flow rate is equal to swept volume for only ideal compressor. This point keep in mind. Okay. So if you look now, if I have the volumetric flow rate, I can always find out the mass flow rate. Okay. So this is the volumetric flow rate at the suction or at the inlet volume that is being sucked into the cylinder, or volume flow rate that is measured at the inlet of the compressor. So if I know the volume flow rate, I can find out a mass flow rate. How to find out a mass flow rate from volume flow rate? You can multiply it by density, or you can divide it by the specific volume. So to get mass flow rate, I have used this equation. M mass flow rate M dot is equal to Vs. Vs is the volumetric flow rate of the compressor divided by V1. V1 is the specific volume at state 1, inlet condition. Inlet, whatever is the specific volume, that specific volume, if I divide the volumetric flow rate by a specific volume, I get a mass flow rate of the compressor, given compressor. Okay. So one parameter, volumetric flow rate, we have determined. Now look at another important parameter, that is work input to the ideal compressor. So how to find out work input to the ideal compressor? As we have seen, it can be found out from the PV diagram. So PV diagram for the ideal compressor is shown here. Okay. So to find out area enclosed by the cycle 1, 2, 3, 4, what we have to do? We have to find out this area. So this area can be found out either by integrating the curve. Okay, you can go for an integration PV, do the integration for processor 3 to 2, 2 to 1, and then subtract integration, do the integration for 4 to 1, subtract this part. So then you will get. Other way of doing it is, instead of doing integration PdV, you can do VdP. So if I do that, so if you see here, work done will be equal to integration VdP over 1 to 2. So if you see here, area of the curve about P or Y axis, right? So when we integrate the curve, we have studied in your PUC or engineering, the area can be found about Y axis as well as X axis. Instead of doing in all the cases, what we used to do whenever we did a PdV, it was about a V axis or X axis. Now what we are doing, we are integrating the curve about Y axis, or here it is pressure axis. So if I integrate this curve about the pressure axis, I will get area under the curve 1 to 2. So that is nothing but area enclosed by this entire cycle. So I will do this integration. So to carry out integration, first I should know what is the process 1 to 2. Right? The process 1 to 2 can be isothermal, adiabatic, or polytropic. All three possibilities are there. Right? So if it is adiabatic and polytropic, the mathematical treatment is same. Only thing is, for polytropic process you have this n index. For adiabatic process, instead of n I use a gamma. But if it is an isothermal process, then the treatment is entirely different, because for an isothermal process PV is equal to constant. Whereas for polytropic and adiabatic process, PV to the power n is equal to constant. So this difference makes the treatment entirely different for the two cases. So let's assume that a process is isothermal. If the process is isothermal, so what I will do, now I will substitute for an isothermal process. I know that PV is equal to constant, or you can say PV is equal to P1V1. Okay, if you do that, then I can substitute V in terms of P. So then it will become V is equal to P1V1 divided by P. Okay, so I have substituted here for V by P1 V1 divided by P, right? So integration of P1 V1 divided by P. P1 V1 is constant. They are conditions at state 1, right? P1 V1 divided by P into dP. So if I do this integration, here P1 V1 are constant. I know that they don't change. Only P varies from 1 to 2. As the air is compressed from state 1 to 2, only pressure varies. Initial conditions don't change. They remain as it is. So therefore P1 V1 can be taken outside. So if you do the integration, so integration of dP by P will be natural log of P, and then substitute the upper and lower limits, you get a P1 V1 log of P2 by P1. Okay, this is the work done for an isothermal ideal compressor following an isothermal compression. So, or it can be, the output can be written in terms of a volume. Then it becomes P1 V1 log of a V1 by V2. So if the process is a polytropic or adiabatic, then PV to the power n is equal to constant. Now let's do the integration for this. So second case, for a polytropic process or an adiabatic process, for both the same treatment can be done. So let us do the same process. Let's integrate. The work done is given by integration, by integrating. So here the pressure is integration VdP. So if I take VdP, I substitute for P. Once again I substitute. So for P will be P1 V1 to the power n divided by P, right, whole to the power 1 by n, right. So this P1 V1 can be taken outside. So then it becomes a dP by P to the power 1 by n, right. So integration of that will be this P1 V1 to the power 1 by n I have taken outside, and I have integrated dP by P, right. So if I integrate that, this is a P to the power minus 1 by n, so plus 1 I do it. So this integration power I take it here, 1 divided by 1 minus 1 by n plus 1, right. So if I simplify this, simple algebra it is. So if I simplify this, 1 minus 1 by n, this will become n minus 1 by n. Okay. Similarly, this will become n minus 1 by n. So that can be written as n by n minus 1. Right. Next step, I substitute upper and lower limits 1 and 2. So therefore I get a P2 to the power n minus 1 by n, P1 to the power n minus 1. Other things are same, no change here. Okay. So if I do that, then what I will do, so I will take, I will further simplify. So how to further simplify is, I will take this P1 outside. If I take P1 outside, so what will happen? I will take P1 outside, this will become minus 1. This will be P2 by P1 to the power n minus 1 by n, right. I have P1 I have taken outside, so I will write here P1 to the power n minus 1 by n, right. So this term I simplify. If I simplify, this will become 1 by n into V to the power n to the power 1 by n. So n gets cancelled, it will become V1. This P1 will become P to the power 1 by n, right. So now if I simplify this and this, powers I will add when they are multiplied. This is P1, this is P1. So both I will multiply and simplify. When I simplify, what I will get is n by n minus 1 into P1 V1 into P2 by P1 to the power n minus 1 by n minus 1. This is what we get. Okay. So here P2 by P1. P1 is the inlet pressure, P2 is the exit pressure of the compressor, right. So P1 is inlet pressure, P2 is exit pressure. So this pressure, exit pressure to inlet pressure ratio, is known as the pressure ratio of the compressor, which is designated as with a symbol Rp, right. So that we can write, or just simply write it as a P2 by P1. So now if we look at here P1 V1, right, from ideal gas equation we know that PV is equal to MRT, right. So that we can substitute here, right. if you substitute that, so this will become n by n minus 1, this will become mrt1, right? For an initial state, p1 v1 is equal to mrt1, temperature at a state 1, right? This can be further simplified. Why? Because we know that pv is equal to mr, right? So here one more thing, please keep in mind, whenever I use capital V, that means it is a volume. If it is small v, it is specific volume. Okay, that's that difference you know, guys, right? So this is a work done. This is an equation for a work done in an ideal compressor, right? So either you can find out using the, if you know the inlet temperature and the pressure ratio, you can find out work done, or you know the inlet pressure and the inlet volume flow rate, then also you can find out. Either way you can do it. Either you can go for, here you can replace this V1 by volume flow rate. This is work done per cycle. What we get here is per cycle. If you get per second, what is the volume flowing? If you substitute this by V1 instead of V1, if you get the, if you substitute this with volume flow rate, what we get is power, right? Similarly here, instead of a mass, if I write it with a mass flow rate, I get a power requirement of the compressor, ideal power requirement of a compressor. So in the next class we will discuss a ideal compressor with a clearance. Okay. So time being, you go through this basics what I discussed for compressor. Then the next class we will discuss about the ideal compressor which has an clearance. Okay, we'll stop now. Thank you.